Imagine this scenario. There is a front-end application that talks to a backend which uses a database. Simple. Now, I am working on the code of that backend application. I neither have nor care about the code of the front-end app, and I do not have the database running locally. All I want is to write the code of that backend application and see the outcome of my work, either directly or through the front-end, the one that I'm not running, and I want that local code to be connected to the database, the one that I'm not running either. All those are set up in a staging environment, but the code I'm working on is on my laptop. Now, I can open the front-end application running in staging environment in a browser. The message saying that this is a silly demo is coming from the backend application running in that same cluster. On my laptop, I changed the code so that the response says something else, and I want to see it in action. Now, let me open that same front-end application again, the one running in a remote cluster. Boom! That front-end running in a Kubernetes cluster automatically decided to ignore the backend running in the same cluster and send a request from the cluster into my laptop, which responded with a message saying that this is a silly demo with mirror_d. Today I will show you potentially the cheapest, the most effective, and the easiest way to develop applications while being able to run them under very similar conditions as if they're running in a production-like environment. My hope is that by the end of this video, you will likely change your opinion on how to set up and run development environments. Now, I'm eager to jump straight into it without much pep talk, but before I do just that, I need to set the scene so that you understand the type of production-like environment I am running, and that has no direct connection with the development environments we will explore very soon. Before we dive into what's, in my opinion, one of the best and most effective ways to set up a development environment, we should take a quick look at the production-like environment I already set up. That might be boring and you're likely already familiar with the setup you're about to see. Nevertheless, I feel that it is important to understand how my environment is set up before we dive into the main subject. So bear with me, I will do my best to be brief. Before we begin, bear in mind that the environment I'm about to show has nothing, and I repeat, nothing to do with development. It is a staging environment that mimics production. Actually, that's not the case. It's a demo environment. I cannot show you my real production, so it is a simulation of such an environment that is not meant to be used for development. Now, with that out of the way, let's start by taking a quick look at what I have in my staging environment. That is a relatively simple one. We have a front-end app that talks to a backend. There is also ingress for external traffic to both the front-end and the backend, and services for internal traffic. The backend in turn is talking to a database running somewhere. Since that database is managed by Crossplane, we can see what it contains by tracing the claim that created it. We can see that there is managed database PostgreSQL with its own network and router. In this specific case, that's PostgreSQL running in UpCloud, which you might want to try out if you haven't already. It's easy to use and it is cheap. It provides Kubernetes as a service, database as a service, and others. You can manage whatever you need through their web UI, CLI, Terraform, Ansible, if you're desperate, and Crossplane, my favorite. Try it out if you haven't already. Nevertheless, today we're not talking about UpCloud. I'm mentioning it mainly to stress that the app we're using today uses a PostgreSQL DB hosted in UpCloud, and if you are following along, you'll find instructions to reproduce what I'm doing in other providers like AWS, Azure, and Google Cloud as well. Now, going back to that claim, it created two objects, one being a resource that manages the schema in the database through the Atlas operator, and the other a Kubernetes secret. We also created a database called main in that PostgreSQL server running, in my case, in UpCloud. As you can see, I have a typical three-tier application with a frontend, a backend, and a database. There is nothing special about it except that you would have trouble setting it all up locally, especially since those are likely to be connected with other applications running in the same cluster. So there's more than those three. As you will see soon, there will be no good reason to work locally. I could even say that working locally would be a silly complication without any tangible benefit and quite a few downsides. We can see all that in action by opening the frontend. There are two things in that frontend we should note. First, we can see that the header says this is a silly demo. The important part of that observation is that the text in front of you is not static. It comes from the backend. Frontend made the request to the backend, asking it for information, which responded with that message, and the frontend displayed it on the screen. Simple. All that is, of course, silly. I did it that way mainly to demonstrate the communication between the two. As you will see later, that silly message will become very, very important soon. Second, if you click the Add Video link, type something as the ID and the title and click the Add Video button, the frontend sends that information to the backend, which in turn stores it in the database, thus showing that all three components are connected. Similarly, we can send the request directly to the backend, and we can see that the backend, when used directly, responds with the same "this is a silly demo" message, the one we saw in the frontend. Second, we can send another request directly to the backend, but this time with the intention to retrieve data from the database. We can see that the output contains the data we previously introduced through the frontend. Okay, now that we have the scene set up, let's see how we can develop one of those components while still leveraging the existing production-like environment we just saw. The main premise is that we want to have a development environment that is as close to production as possible. At the same time, there is one important requirement. One person's work should not affect other people. Whatever I am developing should not impact other developers. No action of mine should affect other. So, I cannot use the staging environment directly, nor I should be able to replace it with my code, nor I should be able to affect data in the shared database, nor do anything else that affects anyone else. All that means that I and everyone else should be able to develop in isolation while still having the setup that resemble production. Right now, I'm already inside the directory where I cloned the repo of the backend application, and let's say that I would like to change the message we saw earlier. I'll do that by modifying that message in the root Go file. Now, to be clear, don't freak out when you see Go code. I'm using it only as an example. It can be applied to any language, so it doesn't really matter. I just needed to change some code. Next, let's say that I would like to see the outcome of that change in form of the application running in, more or less, the same way as if it's running in staging, which acts as a production-like environment. I can do that with mirror-d. Here's an example config. The target points to the deployment of the backend application running in the staging namespace. Further on, we are instructing it to mirror the traffic coming into the pods created by that deployment in the remote cluster. Finally, since, as we will see very soon, mirror-d needs to run an agent, we are instructing it to run it in the namespace staging as well. And that's it, for now at least. So all that's left is to run mirror-d that will exec using the config file. It will run air, which monitors local file system, and will execute go run every time we make any change to the source code. We can see that the application we're working on is running locally. It is not running in that cluster, but locally on a laptop. That part is very important. The curious thing, actually really curious thing, is that we can see some requests coming into the application running locally. What is sending those requests? Why is my application running locally receiving requests? I'm certainly not the one to blame. I'm not doing anything, yet requests keep coming in. How is that possible? Can you guess who or what is sending those requests? Here it goes. Those requests are coming from the remote application. The pods have health checks that are periodically sending requests to the app. Since we are now running a variation of that application running locally, through mirror-d, it is mirroring all requests coming into the remote application to the local version we are running on a laptop. That being said, our goal is not to see health checks being mirrored to the local process, but to use it to simplify and improve development. So let's do just that. We will leave mirror-d running and open a new terminal session in the same directory. This project uses DevBox to bring in the tools we might need and stores a few environment variables in env. So let's start a new DevBox shell and source the env file. Now, let's start for real this time by sending a request to the local process first. As expected, we got the output that matches the changes we made to the code earlier. Here comes the question. What will happen if we send the same request to the remote process? To make things easier to track, we'll add something equals else as query parameters. If you take a look at the logs of the local process, we can see that the request sent to the remote process was mirrored to the local one. That means that we can observe what's happening in logs or place a breakpoint to debug it or anything else we might be doing while developing, except for one thing. The response from that request came from the remote process. That's essentially the same result as what we observed with the health checks. Incoming requests are mirrored to the local process, but the responses are coming from the remote one. Both processes are receiving the same requests, but only one of them is responding. Now, we'll change that soon. For now, let's see what's happening with the database. We can, for example, send a request to the local backend process, I repeat, the local backend process, to add an entry to the database. How did that work? We're not running a database locally, and even if we would spin it up, we did not configure the local process with the database credentials. Here it goes. When we started the local process with mirrord, it, among other things, added the same environment variables it found in the remote counterpart. Given that the code itself uses environment variables to connect to the database, the local process itself is now talking to the same remote database as the remote backend. And we can confirm that's really the case by sending a request to the local process to retrieve all the records from the database. We can see that there are two records. The first one was the record we added to the database through the remote frontend that talked to the remote backend, which in turn added it to the remote database. We added that record before we even started using mirrord. The second entry from that remote database was added through the local process, thus proving that both are connected to the same database. Finally, we do not even have to interact with the remote process directly. Let's see that through the remote frontend. The first thing you'll notice is that the header in the frontend is still stating that this is a silly demo, the one without mirrord, meaning that responses are coming from the remote backend. However, if you observe the logs in the local process, we can see that the frontend request that was sent to the remote backend was mirrored to the local backend process as well. So here's what happened. We sent a request to the frontend, which sent another request to the backend. Mirrord detected that incoming request and mirrored it into the local process on the laptop. Both the remote and local backend processes processed that request, but only the remote process made the outgoing request to the database to retrieve data, and only remote process responded back to the frontend. As a result of all that, we have a local process that is fully integrated into the system, and we can observe what is happening with our local code through logs, or we can put breakpoints if we would like to debug it step by step. We did not have to run the frontend or the database locally, nor to fiddle with local configuration. Our local process is configured in the same way as the remote one, and requests are being mirrored. Now, all that is nice and dandy, but, and this is important, more often than not, observing logs and debugging the local process is not enough. We might want it to respond as well. We might want it to steal, not mirror, but steal requests. Let's take a look at a slightly different mirrord configuration. The only difference when compared with the previous config is that this time we set feature network incoming to steal. So let's run it just as we did before and see stealing in action. Next, we'll execute the same request against the remote process as before. This time the response is different. This time, even though we sent a request to the remote process, the response came from the local one. The response message is based on the code changes we made earlier and that were not, and I repeat, not deployed to the cluster. Let's see what we'll get if we open the remote frontend in a browser. Look at that. The frontend header text now changed. It says that this is a silly demo with mirrord. So we open the remote frontend, which just as before sent a request to the remote backend, but this time, however, mirrord stole that request and sent it to the local backend process, which responded back to the remote frontend. This time the header in the frontend says that this is a silly demo with mirrord, confirming that requests are now responded by the local process, no matter whether those requests are sent directly to the remote backend or through some other app like the frontend. That, however, might not be enough either. since such a setup might result in you being hated by your teammates. They might accuse you of messing up with the staging environment because they're all going to see the response from your local code. The problem we have with the current setup is that all requests sent to the remote process are stolen by the one running in our laptop, in my laptop. Assuming that we are not the only person using that production-like environment, such a setup might affect others. We need to figure out a way to limit this setup only to the person who created it. Fortunately, there is a solution for that as well. Let's take a look at another variation of the mirror config. This time we added HTTP filter to the remote incoming feature. We can specify quite a few ways to filter requests that should be stolen. Today we are going with a simple one that uses path filter with the regular expression, which will include only those that have the query parameter user set to vfarsec, which is me. Let's execute it first. And now let's say that someone else is using the staging environment and sends a request to the backend. We, or that person, got the response from the remote backend that did not involve local process. From the perspective of that user of the staging environment, there is nothing beyond the remote process. That person would not even know that we are stealing requests. On the other hand, I can send a request to the same backend application with the addition of the query parameter user. This time, the request was indeed stolen by mirrord and sent to the local process. We can see that both in the response as well as the logs. If we placed a breakpoint in the code, we could have started step-by-step debugging or do whatever else we might want to do to ensure that our local code is behaving as expected within the context of the whole system. Similarly, someone else might open the frontend. That person would not see anything special since the frontend would be sending requests to the remote backend. We can see that through the header text retrieved from the backend. On the other hand, I can open the frontend with the query parameter user set to vfarsec. This time the frontend also sent a request to the remote backend, but that request was stolen and forwarded to the local process, which responded with "this is a silly demo with mirrord," the one that is shown on the header text. Now, to be clear, in this setup, mirrord is oblivious of the frontend. I had to modify the code to ensure that user parameter is sent to the backend. Otherwise, that parameter would not be included in the request frontend sends to the backend, and it would not be stolen by mirrord. So, some changes to the code, minimal ones, might be required. There is much more to mirrord. For example, if the remote process is working with files, the local process would be accessing those same remote files just as it uses the same environment variables. Just as we are manipulating incoming requests, we could have configured it to manipulate outgoing requests as well. There are also VS Code and IntelliJ extensions in case one dislikes executing commands from a terminal. Finally, everything we saw and talked about is open source with MIT license. On top of that, there are additional commercial features you might want to explore. You might be covered with open source or not. It all depends on whether you need or do not need those additional features. For example, stealing works only with HTTP requests. If you're using HTTPS, as you should in production-like environments, you might need to look for team or enterprise editions. If you want to debug an application while others are debugging it, open source will not be enough. Similarly, if you're using messages and queues in your application, as you should, and you want to decide which messages go where, you might need to use the queue splitting feature, which is reserved for the commercial edition of mirrord. And so on and so forth. Long story short, if you work in a team, as most of us do, there is a strong chance that you might need a commercial version. That being said, I feel that mirrord strikes a healthy balance between open source and commercial offerings. You can accomplish the main goals with open source, but you will be even more productive and will not have to make any sacrifices with one of the commercial versions. Okay, now let's switch gears and talk about pros and cons. Let's start with negative parts of mirrord. To begin with, it does not always work, which is a strange statement to say, but it doesn't always work. When an agent is starting the application that we are mirroring or stealing from, that application might be unresponsive for a few moments. Not long, but few moments. That short unresponsiveness should not be a problem for the person starting mirrord, but might affect other people working with the apps in that same cluster, or if you're executing automated tests, as we should, they might fail due to those networking glitches. Next, there are cases when mirrord might stop working altogether, or to be more precise, it might not mirror or steal requests. In those cases, remote processes are not affected since mirroring and stealing might not be happening, but the local ones, yes. And I had to restart those remote pods to fix it. There might be a better way to deal with those situations. Still, no matter what the workaround is, it might happen that it is just not working, that it just stops working. It's not a common thing, but it happens. Finally, documentation is often confusing or insufficient. I could not figure out why I might want it or how to start using mirrord right away. Later on, once I passed that initial hurdle, the rest of the learning process through the docs was relatively easy and straightforward. Everything we might need is there, but not necessarily organized well, especially the quick start, which does not really result in any start. After all, mirrord is an easy tool to use with relatively simple configuration, so extensive documentation is not critical. It just might be complicated to do the first steps, that's all. Now, none of those cons are really deal breakers. The issues are likely to be fixed and docs will probably get better. And none of them should prevent you from using it or getting value from it. As for pros, to begin with, mirrord allows us to have a production-like development environment. That is huge, since that allows us to catch issues we would normally not see if we would be using something like Docker that behaves completely differently from production, assuming that your production is in Kubernetes. Similarly, it saves us from trying to replicate a production-like environment in a local cluster like Kind or Minikube. Mirrord allows us to connect to any other service that remote process we are mirroring or stealing from is connected to. It essentially allows us to run a process locally with that process behaving as if it is the remote process. Filters are probably the most important feature. One thing is to mirror requests completely. And completely different thing is to ensure that mirroring does not affect other people using the same remote environment. What else? Yeah, mirrord is very, very simple, yet at the same time very feature-rich. By being able to mirror and steal both incoming and outgoing requests as well as to share environments and files, we probably have everything we might need to make local processes act as they are running inside the cluster. Finally, there is low resource cost. The solutions that enable us to run development environments inside clusters tend to increase the cost through additional resources they are using in those clusters. Mirrord agent also runs in remote clusters, but it is likely using less resources than if we would be running copies of our own applications inside those clusters. All in all, I think it is awesome and a valuable addition to our tool belt. To be honest, I was not positive towards it from the very start due to, in my opinion, silly quick start. However, once I got my head around it, which did not take long, I can say that I love it. It's great and you should give it a try. See you in the next one. Cheers.